All right, so homework 11 is due tomorrow. Okay, so it's less than 2 days now. And then next one will be due on Monday. And final exam will be on Thursday at 10 o'clock. Okay. For the classroom disinfection, I'm asking Anthony and Joshua today. Okay. So we'll take a quick look on what we learned last time. So last time we took a look on how to trace images by using ray diagram. So if you have prime mirrors, you can pick 2 points from the object, and then you can draw 2 rays out of that point, and then you can apply law of reflection. You can locate the image of the 2 points, and then therefore you can locate the image of the whole object. Okay, and it will turn out to be distance of the object will be equal to distance of the image, and the image will be upright. It will be a virtual image from geometry there. Okay. We also took a look on spherical mirrors. You can make spherical mirrors by cutting a small piece out of a sphere and then made one side of it to be mirrored. If the outside here is mirror, it's called convex mirror. If the inner side on the other side is mirror, then it's called concave mirror. Okay. For spherical mirrors, there's a central axis that goes through the center of curvature and towards the center of the mirror. So that's called central axis or principal axis. And then the center of curvature here from this to there, this should be the distance equal to r. With that, you apply law of the reflection for a ray or several rays. In this case, parallel rays hits the mirror here, you'll get reflected backwards. So according to law of refraction, this instance angle, this is a normal direction if you have a line connecting the center of curvature to the surface, to the point on the sphere here. That's the normal direction. So those 2 angles will be the same. And the fact that this is parallel to the center axis, so then this angle will be theta as well. Okay. So this length will be then the focal length, which will be the same as this guy here. Now the fact this angle is the same as this angle, so then this will be equal to the focal length. Okay. So focal length here plus focal length is equal to 2r. That tells you the focal length is equal to half of the radius of the curvature. Okay, so f equal to half of r, that's coming from there. Similarly, for a concave convex mirror here, you can also prove from the geometry applying, when you apply law of reflection here, these 2 angles are the same. So then this should be the angle theta. This should be also the angle theta. So then this is the length of the same as this guy, which is the focal length. So twice of focal length is equal to r. Okay. So in that case, focal length for a convex mirror is equal to half of r, but with a negative sign, because the rays, reflected rays, if you have them on a convex mirror, they will not physically meet at the focal length. So you get negative r there. For a concave mirror, if you have parallel rays hit the mirror, they will actually meet physically at the focal point. So then the focal length is positive in that case. Okay. You can use 3 principal rays to locate the image. So those 3 rays are parallel rays, means the array that is parallel to the center axis. A focal ray is a ray goes to the focal point, and then a center of curvature ray called C ray is the ray goes through the center of curvature and hit the mirror. For P ray, it hits the mirror, get reflected back through the focal point, and then the focal ray F ray hit the mirror will get reflect back parallel to the center axis. C ray will hit this and come right back because that's the normal direction. So law of refraction will tell you you'll get instance angle is 0, so then reflect angle should be also equal to 0 in that case. Okay. If you have a convex mirror, you can also use the three principal rays to locate your image. So in that case, P ray hit the mirror will get reflected, and then this reflected ray will appear to come from the focal point. Okay, and then for the C ray, it will just go through straightforward undeflected, because that's in that case incident angle is 0. Okay? F ray that appears to go through the focal point, but it will be reflected in the parallel direction to the center exit backward. Okay. You can pick any of those three principal rays to locate your image, because two line will determine a point. All right. For concave mirrors, depending on where your object is, you'll get real image. You can also get virtual images. So if you are beyond the focal point, that means the DO is greater than focal length, then you'll get, in both cases, you'll get real image. That means the refracted ray, they do physically meet at one location. Okay. So if you are beyond the center of curvature, you get a reduced image, real image. If you are in between center of curvature and focal point, you get a enlarged real image. Okay. If you are within the focal point, so DO less than focal length, then you will get a virtual image instead of real image. Okay. And in this case, it's actually an enlarged virtual image. And we derive the mirror equation by looking at the two pairs of similar triangles. So the mirror image is 1 over DO plus 1 over DI equal to 1 over F, where DO is the distance from the mirror to the object, and DI is the distance from mirror to the image. F is the focal length. Okay, this also applies to convex mirror. Although we derived it from a concave mirror, but it also apply to a convex mirror. The magnification is defined as the size of image divided by the size of the object. It's also related to the distance of image and distance of object, okay, with a negative sign there. So I think that's what we learned last time. Today we are going to take a look on images formed by refraction. Okay, so for mirror images, there are images formed by reflection. In this case, we'll be taking a look at images formed by refraction. So if you have a ray hits the surface of a transparent material, part of it will be reflected and then part of it will be refracted. Okay, so that means part of the light will go into the median. So in that case, let's take a look on if we're zooming into the surface over here. If you have an object in front of this curved surface of a transparent object, then you'll see you can use two rays to hit on the surface, and then you can find its image, okay, to be somewhere here. You can take a ray that is hitting on the surface in the normal direction, which means this is the center of curvature. That ray will go through the center of curvature. So incidence angle and refracted angle will be 0. You can take a ray that hits the surface over here, and you can apply Snell's law here as well. So N1 sine theta 1 will be equal to N2 sine theta 2. You'll see in this case, if this surface curved outward, then you'll get a physical point or a real image inside the median, okay? So in reality, the optical components you see often will be called lenses. That's to form images with Snell's law or law of refraction. Two major types of lenses you will see. One is called converging lenses. That means these lenses will converge rays. The other one are called diverging lenses. That means they diverge rays. Okay, in this class, we will focus on this type of lens called double convex, or this one, double concave. Okay, if not otherwise stated, we'll be just focusing on when we are referring to convex lenses, that means we are referring to the double convex lenses. If we are referring to concave lenses, we are talking about double concave lenses. Okay. All right. So for convex lenses, actually, it will converge rays. So if you have rays parallel to the axis hit on the lens, then it will be get focused. They will be get focused onto the focal point. Okay. And this is similar to if you have two prisms, you put them in this arrangement, the rays can be, oops, going too much, can be converged, okay, in that sense. On the other hand, if you have concave lenses, then parallel rays will be diverged. They appear to be coming out from the focal point in that case, okay? And then this is similar to have prisms in this orientation here, so then they will diverge the parallel rays, okay? Similar to what we do to the spherical mirrors, you can use three principal rays. Okay, here we use P ray. Again, that's the parallel ray to the axis of the lens. F ray refers to if the rays are coming from a focal point or appear to be going through a focal point in that sense. Okay. Instead of using C ray, center of curvature ray, we'll use midpoint ray here. So midpoint ray, they go through the middle of the lens directly without being deflected. Okay, similar to the center of curvature ray in that sense. Okay, will not be deflected. All right, let's take a look on how to draw the ray diagrams here. So for a convex lens here, if you have an object somewhere here, you can use those three rays to locate its image. So P ray hits the lens and it will be converged through the focal length. So the refracted ray will go through the focal length. Okay, midpoint ray will just go through straight. Focal ray goes through the focal point and then will be reflected parallel to the center axis. So you can find its image somewhere here. Okay, actually you just need two of those three rays to determine the object. Okay, so you can use any two of those three. Similarly, for a concave lens, if you have a object over here, the P ray parallel ray to the axis will be reflected in that direction, appears to be coming from the focal point on this side. The F ray appears to go through F, the focal point, but it will be refracted parallel to the axis. Okay, and then the mid ray will just go right through. So you can see those three rays, they are further diverged, so they will not meet physically on this side, but they will appear to coming out from a point somewhere here, okay, on this side. So this will be then the image, okay, somewhere here. It's going to be a virtual image because those three refracted rays, they do not meet physically, okay, but they appear to come out from a point on the other side. So it's a virtual image. All right. So then in this case, if this is a concave lens, you'll see the image will be here. So it doesn't depend on where your object is. If this is a concave lens, you're always going to get a virtual image, okay, for concave lens. Now this is the other way around. For mirrors, concave mirrors will give you, could possibly give you a real image and then also virtual image as well, okay? For convex lens, then you will be able to get real image and sometimes also virtual image. Depends on where your object is. If you are beyond the focal point, then you are going to get a real image, okay? And if you are inside the focal point, that means your DO is less than the focal length, you are going to get a virtual image, okay? In this case, it's an enlarged virtual image. Okay, you can see, you can just use two rays here, a midpoint ray and a parallel ray to find its image. You can also use any two of these to find the image, okay? So to summarize, you can have three types of image formed by lenses, thin lenses, in this case. So the first case is if your focal length is positive. So that refers to a convex lens. Then in the case of your object is beyond the focal point, you get real image. So then because this is real image, DI will be positive. The magnification then will be negative because it's upside down image. Okay. So HI is negative, HO is positive in the case M equal to HI over HO. The second case, this is again, if you have focal length is positive, which means convex lens. But if you have object that inside the focal point of DO less than focal length, then you'll get virtual image. Because it's virtual image, DI is negative. Magnification is greater than 1 in this case. For the third case, it's referring to if you have a concave lens, then it doesn't depend on where your object is. You're always going to get a virtual image. And then DI is negative because it's a virtual image. Magnification will be less than 1. That means your image is reduced. Okay. For thin lenses equation, so we can take a look on this object here. If it's somewhere here, we are going to take a look on the case if object is placed beyond the focal point. So you'll take a P ray here, you'll hit this guy and then get refracted going through the focal point. So this is where your image is. You can determine the position here by drawing a midpoint ray here. So the two ray will meet here. So this is your image, okay? Now take a look on this triangle and this triangle. So these two angles are the same. So then you'll have a pair of similar triangles here because they are both right angle triangle, okay? Also, if you take look at the triangle of this guy and then this guy, so this is also a pair of similar triangles. You can use two pair of similar triangles the same way we did to derive mirror equation. Okay, you can do the ratios of the side from one triangle. So you can do HI, say over this guy, and then that should be equal to HO over this guy. And then you can do also HI over this DI will be equal to HO over DO, okay? You can use those two equations, you can derive this thin lens equation, okay? So I'm not going to repeat the derivation because it's similar to what we did last time. The result will be the same. So thin lens equation and mirror equation, they are having exactly the same expression, okay? So 1 over DO plus 1 over DI is equal to 1 over F, where DO is the distance from the object to image to the mirror, and also DI is the distance from the image to the mirror, okay? F is the focal length. The magnification is defined the same way we did for mirror images. It's equal to the size of the image divided by the size of the object, and then that's related to minus DI over DO, okay? All right, so those equations are the same. Let's take a look on, or actually not yet. Let's take a look on sign conventions here before we take a look on the example. So sign conventions for lenses. So if you have a convergent lens, which means convex lens, then the focal length will be positive, okay? For a divergent lens, the focal length will be negative, okay? Magnification is positive for virtual images or upright images. Magnification is negative for invert images or real images. The image distance is positive if you are getting real images. The image distance negative if you are getting virtual images. Okay.
Okay.
The object distance is positive for real objects. And the object distance is negative for virtual objects. Okay, so the last two conventions for DO, let's refer into if you have multiple lenses. So then in that case, images can also, so images coming from the first lens can also serve as object for the second lens. Okay, so that's two is referring to. Okay, so in the case if you have an image, a real image serve as the object, then DO will be positive. Okay, if you have a virtual image serve as the object, then it's going to be negative. Okay, so this referring to this guy here. All right, so we will take a look on this example here. This one says, if you have an object with a height of 2.54 centimeter, which is an inch, if this is placed 36.3 millimeter to the left of a lens with a focal length of 35.0 millimeter, asking you A, where is the image located, and then B, what's the height of the images, okay? So you can use the thin lens equation and the magnification equation. You should be able to solve for this one, okay? I'll give you guys a couple minutes to try this, and then we can take a look at the solution after that, okay? All right, so let's take a look here. So it tells us the height of the object. So that's HO, size of the object, 2.54 centimeter. It tells us that this object is placed 36.3 millimeter to the lens. So that means DO is that. And then it says the focal length is 35. Okay. So you can draw a ray diagram to help you visualize the problem. You can put just an arrow as the object here. You can say, so this is 35. So this is focal point somewhere here. And then also focal point on the other end here. If you put a parallel ray, P ray there, and it will go through the focal point, okay? And then you can put the center of curvature ray, so go into the center of, or the midpoint ray in this case, we'll go that way, okay? So it looks like it's going to be, these two are going to be intercept at some distance, relative large distance there, okay? But let's take a look here. You can apply this equation, right? Because you're looking for DI, you have F, you have DO, so you can solve for DI there. So 1 over DO plus 1 over DI equals to 1 over F. You're looking for DI. So 1 over DI is equal to 1 over F minus 1 over DO. Okay. To solve for your DI, this is 1 over it. So you do inverse of that. That should be equal to the inverse of the other side. So DI will be equal to 1 over F, 35.0 millimeters. Sorry, that should be millimeter as given. And minus 1 over 36.3, also in millimeter. Okay. And you do inverse of it. So then this will give you 977 millimeter. Okay. So it looks like it's going to be, DI is going to be very large. That's in agreement with the sketch here. So it appears to be like the two reflected ray will meet some large distance. Okay. For your second part, it's asking you what's the height of the image. So you're looking for HI. This equation doesn't have HI in it. So this one here, you'll see that you're given HO, and now you have DI, you have DO. So you can solve for that. You'll be looking at this part of the image magnification equation there. So you can set up that way, HI over HO equal to minus DI over DO. So then HI will be equal to, you multiply both sides by HO, okay? Minus of 977 divided by DO is 36.3 and multiply by 2.54, that's in centimeter, okay? So millimeter and millimeter will cancel out, so you don't have to worry about converting the units. You can just express as HI in centimeters. So this will be minus of 68.4, that's in centimeters, okay? So it's going to be a very relatively large image somewhere there, okay? All right. Any questions you guys might have? All right. So if not, then we'll move on to the next section here on the vision. Okay. So the fact that we can see object is rays comes off the object hit our eyeball, and then the image will be formed ideally on the backside of the retina here, right? But in case our eye have some defect, say if we have a four-sided eye, okay, then image is going to be formed somewhere here, not on the retina. So we need a collection lens here in this case, okay, to converge the rays to be on here, okay? So this is like over diverged there, then you want to convert it to be on the retina there, right over there, okay? So in this case, a convergent lens is used, a convex lens is used, okay? So this happens when we pretty much like when we get older, then we might have that four-sided problem, okay? And for a lot of young people, like me myself, I'm nearsighted. So that's what happens, like the image of the object cannot be formed onto the retina here. So I need divergent lens here, concave lens, okay, to correct that, to put image right there. Now, also that when you see object that is very far away, it appears to be small. That's because you can see if it's far away, then this DO is very far away. So then this DI is smaller. That gives you a smaller magnification ratio. So image appears to be small. For the same size of object, if you are closer to it, then image is larger on your retina, so it appears to be larger, okay? If you are closer to the object. For microscope, there are several pieces of lenses inside. So the lens that is closer to the object is called objective lens. And then the other piece close to your eye is called eyepiece, okay? So for the objective lens, it's a convex lens. So it will make this image larger, okay? And then you will see that also larger through a second piece here as well, okay? So the image will be further magnified in that case, okay? All right. So for the lecture part, I'll stop here for today. Now, you guys have seen, received the email to do the end of course survey, okay? I see several of you guys have done that. If you have finished that, you can leave, but if not, then take a few minutes to finish that for this class, okay?